Hello, my name is Mason Leist, and on behalf of my fellow co-authors, I would like to welcome you to our poster presentation. As I share my screen and start sharing my slide, I would like to give a little bit of background information on our poster. As commonly believed that every massive galaxy in the universe hosts a central supermassive black hole, but only a fraction of these are considered to be active galactic nuclei, or AGN. According to the unified model of AGN, the central engine consists of a hot accretion disk orbiting a supermassive black hole surrounded by a torus of gas and dust. This torus obscures different lines of sight towards the central engine while absorbing a large fraction of the accretion disk radiation, which is then re-emitted dominantly from mid-infrared to millimeter wavelengths. The torus was long thought to be the dominant source of mid-infrared emission in AGN until recent interferometric observations of several AGN revealed that the majority of this emission arises in a region perpendicular to the torus within the central parsecs. The emerging paradigm now is that the torus is a central structure in a gas flow cycle where some material is accreted to the supermassive black hole and some is driven out in a dusty wind. The Galactic Activity Torus and Outflow Survey, or GATOS, has been awarded prime JWST time to search for evidence of this polar dust with the mid-infrared instrument MIRI. The low surface brightness sensitivity of JWST MIRI should reveal this polar dust structure, while additional simulations have shown that deconvolution could reveal this structure below the resolution limit of the telescope. Our work aims to determine the optimum deconvolution method to accomplish this. Now, to determine this, we need to understand how observations are affected by the complex PSF from the telescope as well as from the MIRI detector. To test this, we have adopted the following study design where we inject a simple model into MIRI-Sim, replicating the GATOS observing campaign, and then injecting the raw output data into the JWST pipeline before attempting deconvolution using a variety of methods. We'll use flux conservation, full half maximum Strehl ratio as merit functions to determine the optimum deconvolution iteration and ultimately the optimum method moving forward as well. Now here we show the JWST PSF from the telescope only generated by WebPSF. Each image corresponds to a filter selected for the observations. And here we show preliminary results of injecting a single pixel into MIRI-Sim, again simulating each image again corresponding to a filter selected by the observations. And right away, we notice a difference between the telescope, the WebPSF, and detector MIRI-Sim PSF generated images at the shortest wavelengths chosen. This crucifix pattern here is attributed to scattering in the detector at the shortest wavelengths, and further studies are needed to understand how this pattern will affect our deconvolution results. Now, this poster reports our current progress. There's still much more work to be done to determine the optimum deconvolution method for JWST. But as we move into the 30-meter telescope era, diffraction-limited observations afforded by extreme adaptive optics systems will become typical. And with the complex PSF expected by those telescopes, we believe that deconvolution algorithms are likely to become more commonly used and important to investigate low surface brightness features. That is the end of the presentation.